Hi, I'm Renee Burton. I'm a data scientist and a threat researcher at Infoblox. I really appreciate being included in the Apricot conference, and I'm sorry that I'm unable to join you all live. I will be asleep by the time you are listening to this presentation, but I'm happy to answer questions or engage in further discussion and collaboration offline after the conference through email. Okay, so what I'm going to talk about today is one of the methods that we are using within our threat intelligence group for reducing the amount of data that our analysts and threat researchers need to look through in order to find threats within our data. Using data science techniques and graph theory methodologies. What I'm going to show today is just a simple look at how these work and discuss a couple of statistics associated with this. It's part of our standard practice now, and it has been part of our workflow for quite some time. So, campaign distillery, we're gonna see how that all works. So the problem we're trying to solve at Infoblox is being able to get as many threat indicators for our customers as possible. We are DNS, DHCP IP management, often referred to as DDI, infrastructure provider, and we have the DNS firewall security, both for on-prem and cloud customers. So like many other people in the security arena, we're providing block lists, which include things like, for DNS, obviously, domain names and IP addresses with threat indicators to our customers. Our strategy for being able to make this as relevant as possible is to be many source. In other words, we're using a wide range of sources in order to aggregate and create intelligence and these block lists that we think are most likely to impact our customers across the globe. One of these sources that we use is spam. So a lot of spam is just annoying and spam and is very well captured by spam filters. But spam is still used for an enormous amount of malicious activity, particularly for information stealers and ransomware. So we're able to leverage that data source in order to find email addresses and command and control systems that impact our customers. And we know that this source is particularly valuable for our customer base because we've been able to study it and the impact on customers for quite some time. The problem is there's a lot of spam in the world and everyone has a limited number of resources. So the question becomes, how can I harvest the data within spam? First, figure out which ones are interesting, which ones are malicious, and then extract the relevant elements in order to add to our security products. How do we do this efficiently given a limited amount of human resources to look at data? So in our case, what I'm going to talk about today is one using graph processing or graph theory. A graph, for those of you who might not be familiar, is just a representation of related data. The terminology that we use in the math world is nodes. Those are subsets of the data, and edges. Edges exist between two nodes if those nodes in some way are related. So there's many different ways in which you can construct a graph in any context where you have a network relationship, which can be very definitive, like this IP address is connected to this domain, or can be very statistical in nature, that this domain is somewhat similar to this domain, or if you were in a different subject matter space. An orange is similarly round to an apple, even though they're not related. You could have an edge between them that indicated the similarity of their shapes. In our case, we are using email metadata. So in particular, the subject lines, sender IPs, file names, that kind of information. You can use a wide range of information here. We're often looking at attachments, so you could use file sizes. You can use all the email header information from the SMTP IP traffic or SMTP traffic. So we're going to build a graph from all the data, and then we're using the graph to group the spam into likely campaigns. I'm going to show you a little bit how that looks, and then talk a little bit more specific examples here. This process, which I'm showing here on the left, is generally how it works, right? So really repeating what I've said on the last slide is we're going to take this spam, which is a very large volume collected all over. We extract these attributes from it. And those attributes really could be anything, as I mentioned. In the examples I'm going to do today, I'm mostly using subject lines and file names, but it could be IP addresses or email content or anything that I have within my data. I'm going to create a graph. I'm creating it all at one time, right? So I'm, tens, hundreds of thousands of emails at once are produced into this graph. And then within that graph, I'm going to compute what is called the connected components. Connected components just means that I take the whole graph and I isolate it into subgraphs or sections within that graph for which every node in that subsection is connected in some way to all the others. So in other words, they're the things that are connected to each other. And usually the graph will separate out into some large connected components, which we'll also call clusters. Those terms are used interchangeably in the graph world. And then often just small isolated or small other connected components or clusters. And then we use that to infer campaigns from the connected components. So in this experiment that we did early on in December 2019, for example, in that case, we're using about 21,000 emails. These all contained attachments. They were specifically chosen, actually. So they're attachments, and they contain some degree of VBA in them. We use the subject lines and the file names for creating a graph. So in other words, we take every subject line for every email, every file name for every attachment. Those are our nodes. All the subject names, subject lines, and all the file names create the set of nodes. And then there is an edge between a subject line and a file name if there exists some email in our corpus that has both that subject line and that file name. We create the graph of all of that. And then we look at the connected components, that is the things that are ultimately connected together by some set of edges. This reduces our data to 866 components. So in other words, we started with 21,000 plus emails, which traditionally we might hand to analysts and say, hey, go find me malicious behavior and grab the bad guy information out of it, which is obviously not scalable. In this case, we're able to find things that are like together that aren't identical, but have a lot of correlation with each other. And that reduces us down to 866, which is still too big, admittedly. The next thing that we do is filter that data for non-trivial sizes. So if there's only one email that exists in our entire data set, and it's sitting by itself, it has a unique subject line and a unique file name, it's not connected to anything else. From our observation, that's a relatively small campaign. It could still be malicious without a doubt. But from a resource perspective, it ends up being a lot of work to go work on those. So we're going to focus on things that have at least a handful of emails in them. And I believe this 101 components comes from having at least 3 separate emails in order to get down to that size, 3 or 5. So at that point, we have 101 things. And now, because our hypothesis is that each of these connected components represents a single spam campaign, many of which will be malicious, some of which will not be, then our analysts only have to look at one file within each of these connected components. It's still 101 in this case, but they can reduce it further in order to prioritize the way they spend their time. In the end, though, even if you looked at 101 individual items, we've reduced the number of items needing review by 99.5%, all with a pre-human eyes processing step that goes pretty quickly. So let's take a look at some of the advantages for this process that we have found in our use of these techniques for reducing data. One thing we can do when we put the data together is capture campaigns a lot more effectively. Rather than looking at individual emails or even a very small amount, we can put them all together over a period of time. And we can see that because we allow for connectivity, we're able to discover things that aren't otherwise observed or known to be malicious. So in this graph, this is a connected component from that data set that is all emotet. And it does contain several days of data here. And it is between subject names, I believe, yeah, subject names and file, subject lines and file names. And then the lines are green if those are in virus total, and red if they're not in virus total. And I apologize for both the red-green colorblindness aspect. I apologize for that greatly, but also for the way that it could be interpreted backwards as red being bad. And in any case, the way this works is that the dominant part here on the right side, which is green, has save the planet .doc in it. Those are seen in virus total and known to be malicious. And over on the left side, though, there's a huge number that are not seen in virus total, not known to be malicious. But we're able to put them all together and understand them as single activity as of emotet through this graph connectivity. And this is a tendency that we see with a bunch of actors. Emotet, who is a actor, also a particular type of actor who has their own infrastructure, who has malware downloaders for information stealing, among other things. They're a very dominant player in malicious spam environment. They have some techniques that make them a bit sloppy. So what happens is you will have file names that will be reused across campaigns that from a subject perspective are really not relevant or related to each other in any way. Sometimes you see the exact opposite happen as well, a subject line that's passed across multiple file names. And so when you look at that data holistically, rather than looking at it as individual events, you see all of this connectivity where, again, about half of the right side are known to be bad and known to be emotet, and then this portion over here was not known. In fact, nearly 50% of these attachments were not seen. So this really allows us to see a variety of not only the campaign, but when we look at this closely, we can actually see tendencies of how certain actors behave, and emotet being a classic one here. This is just to give another example of how we can use discovery over time. Again, the graph itself is actually just a mathematical object. It's not a visualization or anything like that. You can use all sorts of layouts to view that data, but it is often helpful to look at it visually and not just algorithmically. So what we can find over time, if you're used to just pulling up uh, the the graphs from a couple of days of spam or mouse spam, and you look at that over time, you get a good sense of what certain actors look like. Again, Emotet, because they're such a dominant player and they have very specific ways in which they operate, you can really end up seeing that visually. So not for you guys to actually know, but Emotet, when you look at them in this way consistently over a very, very long period of time, they have this tendency to be sort of maybe like, sea creature-y sort of things where they've got these tentacles that connect together independent clusters of information. Very unique in that sense. So whenever you see this sort of big clusters all together, but they trail and attach to each other, invariably that's an Emotet behavior. So these two over here, which are also quite big, are not Emotet. They're very distinct. And then also in this case, this is from May 2020. This case, it's also not Emotet, but it's very, very large campaign. This turned out to be an actor that we discovered called Wordy Thief, or who we call Wordy Thief, who is a Russian spam actor who also works in information stealers only, a very interesting actor that we've been watching for a long time. And we do have a paper published on that and available on the website if you're interested in actor kinds of things. So this we saw and saw that it was not Emotet, but it was very large. And then where we used that for discovery, determined in fact that it was an actor that we hadn't seen previously. We were able to unroll their history and actually track them on a regular basis. Okay. We can also find that we need to use multiple days in order to really see information over time. So what we find here in these three things, three pictures, is if we just look at one day of activity, December 18th for this data set, and I'm just looking at Emotet here. If we just look at one day of activity, we see that Emotet is broken into three distinct clusters here. That's very common for Emotet behavior. Now, if I add in a couple of days and I do December 18th through the 20th, everything starts to come together, and it's actually a single connected component looking like a big piece with another tail off. And then if I look over this, I think it's 6-day period, you get what I consider to be kind of a classic Emotet signature of three big clusters that are just loosely connected to each other. So it gives us a better sense of understanding the full campaign and also how that particular actor might be acting. Okay. So we've been using this in our workflow, as I said, for quite a long time. There are other ways in which we use very similar types of graph processing in order to understand and reduce the analytic burden of large volumes of data. This one is particularly effective for threat research. We worked with University of Washington Tacoma and their graduate program to try and find a better way to isolate these. In the end, overall, this method was generally stronger than the machine learning approaches. We're still hopeful that we'll be able to find other approaches, at least ones to augment this. But for right now, this works really well. And the UWT students and professors have drafted a paper, which is going to appear relatively soon, called Clustering Analysis of Malware Campaigns, which also uses a lot of virus total labels and other approaches to malware campaign identification, trying to advance the science on that in an unsupervised fashion. And that is it. So thank you very much. I, again, appreciate the opportunity. And if you have questions, please don't hesitate to reach out.
Hello, my name is Vadym Tymchenko. I am one of data scientists at Infoblox. Today, I would like to talk about Dictionary DGA, analysis, dictionary detection, and validation techniques we found useful. First, let's talk about DGA overall. What is it and how it's being used? Domain generation algorithms are being used by many different actor types. They are used by large corporations for benign purposes, such as generate workstation and server host names. Another prominent example is Amazon DNS infrastructure, such as an example on the right, AWS DNS-59.co.uk represent domain name which is generated by some algorithm. DGAs are also used by botnets, mainly to identify their command and control center. And botnets are generating a very large number of domains in order to overwhelm the block lists. DGAs are also used by spam and malspam actors, mainly to generate very large volumes of domains. Different actors have different requirements to DGAs, and domains which are being generated are used in a different way. So, for example, benign domains are always resolvable. They are generated once at the time of allocation or registration. And typically, large companies create the algorithm in such a way that there is a very small number or practically no collisions observed. On the other side, botnet traffic mostly non-resolvable. Majority of domains generated by botnets are not return an X domain response code. They are generated very frequently. Every infected machine generates its own set of domains, so they have to be highly deterministic. And they have fairly low collision tolerance. So if some domain happens to already exist, the bot has to identify if it is a command control server or not, and thus introduces some delay into identification. On the spam and malspam side, domains which are generated mostly resolvable, so they are registered. They're generated once in most cases, and very frequently these actors are using throwaway generators. So they just use a generator to create a set of domains, register this set of domains, and then they will use different generator next time or alter this generator in some substantial way. They are highly collision tolerant. They don't really care if some domains exist, and they will just avoid using them. So what is the difference between traditional DGAs and dictionary DGAs? Traditional DGAs create domain names using character level generator. They are highly unique, and on the other side, they are very vulnerable to automated detection techniques. They are typically, these domains have very distinct features such as high entropy, and lexical features are make it easy to identify. For example, ratio of vowels to consonants, number of digits inside of domain names, and so on. Dictionary DGA builds domain name with words drawn from one or more dictionaries. The benefits of these domain names are that such domain names are natural looking. They are much harder to detect. It's very hard to isolate this type of domains in the more generic case. And on the other side, they are less resistant to collisions, and they might be topic specific. So most spam actors might create a dictionary that is specific for some certain campaign. typical dictionary detection and refining process looks in the following way. We start with initial detection, and this might be some set of domains of interest found in malicious spam email, in as a clustering outcome, or any other sources. Then this data sample is being analyzed to identify a pattern or pivot. Then this pattern is being applied to additional rich data sources, such as broadband traffic, some other information sources, in order to find other domains that we haven't seen, but they are matching to the patterns. Finally, the next step is a refine pattern and extract domains which don't belong to the DGA. This process might be repeated several times and finally reported as results. So critical result requirement is a low false positive rate. Let's formulate the problem of dictionary detection. Given a set of domain names, we want to determine minimal size dictionaries that explain these domains. And we also want to identify the rules how words from these dictionaries are being combined. A few basic definitions. Dictionary is a collection of words. Word is a reused sequence of characters. We do not define what specific language it's supposed to be from. Words shall be reused at least 2 times in different domains, just by definition of dictionary. And active dictionary, specifically in the case of time-dependent dictionary DGAs, is a dictionary limited to words that generator decided to use on specific day or time. Dictionary DGA writers use quite a few different techniques to make detection complex. So first, they might be a single or multi-dictionary generators. Sometimes there are some examples of generators which keep sampling a word from the dictionary and append it to domain until certain length is being reached. There are also different word concatenation techniques are being used, starting from very basic concatenation. Sometimes optional hyphen might be inserted. Some words might be truncated either to certain lengths, or several characters might be removed from either end. Overlapping segments removal, when a word starts with the same character that the previous word ended with, this extra character might be removed. Sometimes a numerical component or pseudorandom component are being added. Let's consider a very concrete example, Supperbox. Supperbox is a very well-known simple DGA. It's completely reverse engineered and understood. It generates a different subset of domains every 512 seconds. It uses a single word set per seed, and the word set consists of 384 words. There are 3 different word sets are known in the wild. Let's see what can be learned from it. First, let's take a ground truth sample for a single day. We apply word segmentation technique. Here we just used a simple word segmentation, just choosing the longest common substring and keeping only those substrings which are higher than certain threshold, are found more than a certain number of times. And then we generate list of variants, how words from the dictionary DGA might be segmented. On the right side, we see that in majority of cases, we have unique combination, single variant detected, but in some cases, alternative variants are being found. This represents a problem because alternative variants might form a smaller dictionary, which is also seems to be correct. We could validate this approach using graph technique. So let's build a word graph where nodes are words and two nodes are connected if these words are found as a part of the very same domain. We see a connected component which corresponds to a correct segmentation. This connected component actually covers all the domains that we saw within this day sample. But there is another connected component which shows invalid segmentation. What is interesting about this component is that these words are also correct words. And while it's very easy to identify it in our ground truth artificial sample, in a real world environment, these words might be connected to other non-related to DGA domains. So it becomes a pretty complex problem to identify this type of wrong segmentation and decide which segmentation is actually correct. Another interesting property of Sapobox. Most publications tell that Sapobox uses a single dictionary, but in fact, generator is built in such a way that certain words appear only at the start or at the end of the domain. There is one single exception. There is one seed that seems to violate this rule. It turns out that this dictionary, this particular seed dictionary, contains some words twice. So they will appear at the beginning and at the end of domain name. If we are able to detect this type of property of generator, this allows us greatly reduce number of combinations that might be generated, and as a result, improve false positive ratio of the results. Let's consider another dictionary DGA. This dictionary DGA is one of 5 that we observed in a Wordy Thief malspam actor. And this specific sample contains 14 domains that seem to belong to the very same DDGA. We see that every domain consists of 2 words, and these words are separated by dash. The very same word might be found at the beginning and the end of the domain. So interesting property of this DGA that it uses highly generic words. So can we find anything interesting in association with it? So first we want to expand the data set. Initial dictionary that we have consists of 8 words. And first we filter broadband traffic to extract domains belonging to tld.site. And we want to find only domains that start or end with one of the known words. Overall, there are 132,000 daily records found in a year and a half. And these records actually correspond to slightly over 6,000 unique domains. Now we can apply refinement by using certain constraints. So first, we want to have domains that contain a single dash character. So there are only 2,500 domains remaining. Then we want to keep only resolvable domains. Finally, we split these domains into words, and each word shall be used at least twice, which we have only 187 domains left. And finally, we want to apply the very same rule we observed in previous slide, that every word could be found either in the beginning of the domain or in the end of the domain. So only 55 domains follow this rule. If we build the extended dictionary, now we have 3 additional words we didn't know about. They are actually matching to other words by having the same sense. Literally, they are related. So let's see how extended graph looks like. And this is a graph that covers 55 domains matching to the dictionary. But the question remains, are all of these domains associated with the same DDGA? How we can proceed from here? In more generic way, the question is, if you know the dictionary and pattern, so now what? It still might be too generic for detection. Depends, completely depends on specific dictionary word selection. Typical approach is to utilize whois information, such as when the domain was registered and who is the registrar. Or alternatively, we use traffic observation. What is resolution activity associated with all these domains? Let's see how it looks like. This plot represents activity associated with these 55 domains observed starting from November 2019 until end of March 2020. In the bold characters, we show domains that we had in our original list. The light blue color represents domains that were resolved less than 5 times on this specific day. And dark blue color shows domains which were resolved more than 5 times. What is really interesting here that all of the domains we knew about had specifically had their activity started at November 25th. But if you look carefully, there are several domains that we identified matching exactly same behavioral pattern. Additional observations that we might make here, that a lot of these domains seem to be resolved on the very same irregular intervals. That allows us also to generate a pattern and find some common characteristics of these domains. And some domains were actually used before the day of interest. So they definitely represent somewhat different structure that need to be analyzed. So to summarize everything I described, we can tell that dictionary identification is a complex problem. Domain segmentation problem, splitting domain into words, and removing invalid segmentation, also not an easy one. Finally, there is a refinement issue. Dictionary knowledge greatly improves explainability of results. If you mark some domain belonging to certain DGA, we want to explain why exactly this label was applied. And dictionary and pattern itself might not be sufficient for a reliable detection. We need to involve some additional information to improve the refinement and be able to identify domains which are not related to actual dictionary DGA. And this is all I wanted to describe today. Thank you very much. Bye.